welcome to this problem walkthrough. Today, we'll be tackling LeetCode problem number 1490, clone N-ary tree. In this problem, we'll explore how to efficiently copy an N-ary tree structure while maintaining the relationships between nodes. Let's dive in and break it down step by step. In this problem, you are tasked with creating a deep copy of an N-ary tree. An N-ary tree is a tree where each node can have up to n children, where n is a non-negative integer. The depth of the tree can vary and is not fixed. The tree is represented using a node class. Each node in the tree has two attributes, val, which holds the value of the node, and children, which is a list of node objects representing the children of the current node. If a node has no children, this list will be empty. Your task is to write a function that takes the root node of this tree as input and returns a new tree that is a deep copy of the original. This means the new tree should replicate the structure and values of the original tree, but the nodes should be completely independent objects. The input to your function will be the root node of the N-ary tree, represented as an object of the node class. Each node in this tree will have a val attribute, which contains an integer representing the value of the node, and a children attribute, which is a list of node objects representing its children. If a node doesn't have any children, this attribute will simply be an empty list. The output of your function should be the root node of the clone tree. The clone tree should be a deep copy, meaning that any changes made to the original tree should not affect the clone tree, and vice versa. To clarify the expected behavior, let's look at an example. Suppose the input tree is represented as a nested list, 1, null, 3, 2, 4, null, 5, 6. This input can be visualized as an N-ary tree with the root node having the value 1. The root has 3 children, nodes with values 3, 2, and 4. The node with value 3 further has 2 children, nodes with values 5 and 6. Your function needs to return a deep copy of this tree. The clone tree should have the exact same structure and values as the original tree. For example, the clone tree would look like this: the root node still has the value 1, with 3 children having values 3, 2, and 4. The node with value 3 also has 2 children with values 5 and 6. Even though the structures and values match, the nodes in the clone tree should be entirely distinct objects from those in the original tree. To emphasize, the original tree and the clone tree must be completely independent of each other. This means that modifications to the original tree, such as changing the value of a node or adding children, should have no effect on the clone tree, and vice versa. Now, consider another example where the input tree is empty. This is represented by an empty list, or a none-root node. In this case, the output should also be an empty tree, meaning the function should return none. This ensures that your solution handles the edge case of an empty input gracefully. Here's another example to illustrate the problem further. Suppose the input tree has a linear structure, where each node has exactly one child. For instance, the input might look like this: a root node with value 1, which has a single child with value 2, which in turn has a single child with value 3, and so on, forming a chain down to a node with value 4. Your function should return a deep copy of this tree, replicating the same structure. The root of the clone tree should have the value 1 and a single child with value 2, which has a single child with value 3, and so forth. Each node in the clone tree should be a new object, independent of the corresponding node in the original tree. The deep copy ensures that the clone tree replicates the structure and values of the original tree, but the nodes in the clone tree are completely independent objects. This independence is crucial because it guarantees that any changes to the original tree, such as altering node values or restructuring its children, will not affect the clone tree. Similarly, changes to the clone tree will leave the original tree intact. The problem also comes with a set of constraints to guide your implementation. For instance, the number of nodes in the tree can range from 0 to 10 to the power of 4, and each node's value is guaranteed to be unique within the range of 1 to 10 to the power of 4. Additionally, while the depth of the tree is not fixed, it will stay within practical limits to ensure your solution can execute efficiently. Finally, let's consider the time and space complexity of this problem. To create a deep copy, every node in the tree needs to be visited exactly once. Therefore, the time complexity of your solution should be O(n), where n is the total number of nodes in the tree. As for space complexity, it depends on the traversal method you choose. If you use a recursive approach, the space complexity will be O(n) due to the recursion stack, especially in the case of a deeply nested tree. Alternatively, if you use an iterative approach with a queue for breadth-first traversal, the queue size could also grow to O(n) in the worst case. Additionally, you'll also need O(n) space for the new nodes in the clone tree. Together, this ensures that your solution is efficient and scales well with the size of the input. To begin, let's consider the brute force approach using recursive depth-first search, or DFS. The intuition here is straightforward. We traverse the N-ary tree recursively and create a new node for every node we encounter. This ensures that the structure of the tree is preserved as we clone it. The process starts with a base case. If the root is null, we simply return null. Otherwise, we create a new node that has the same value as the root. Next, we recursively clone each child of the root node and add them to the children list of our newly created node. Once we've processed all the children, we return this cloned node as the result. In terms of efficiency, this approach visits each node exactly once, so its time complexity is O(n), where n is the total number of nodes in the tree. The space complexity is O(h), where h represents the height of the tree, due to the recursive call stack. While this method is intuitive and simple, it does have a trade-off. For very deep trees, the recursive calls could lead to a stack overflow, making this approach less robust in those specific cases. Now, to address the potential stack overflow issue in the recursive approach, we can use an iterative DFS method with a stack. This approach manually simulates the recursion process by using a stack to keep track of nodes to visit. We start with the root node on the stack and proceed as follows. For each node, we create a copy of it and store a mapping between the original node and its copy. This mapping is crucial because it allows us to link children to their respective parent nodes later. After copying a node, we push its children onto the stack so they can be processed in subsequent iterations. Once all the children of a node have been processed, we link them to the copied version of the node using the mapping. Like the recursive approach, this method also runs in O(n) time, as every node is visited exactly once. However, the space complexity increases to O(n) due to the stack and the map used for tracking the nodes. While this iterative method avoids recursion and thus eliminates the risk of stack overflow, it introduces more complexity in terms of implementation and memory usage. Another alternative is to use breadth-first search, or BFS, to traverse the tree. This approach processes the tree level by level and ensures that each node is only visited once. To implement this, we use a queue for the traversal. Starting with the root, we create a copy of the root node and store a mapping between the original node and its copy. Then, for each node in the queue, we process its children by creating their copies and enqueuing them for future processing. As we do this, we also link the children to their respective parent node copies using the mapping. The BFS approach has a time complexity of O(n), as it processes all nodes once, and a space complexity of O(n), where the queue size is proportional to the largest level of the tree. One advantage of BFS is its predictable memory usage, as the queue size depends on the width of the tree rather than its depth. However, similar to the iterative DFS approach, BFS also requires additional space for the mapping, and its implementation is slightly more complex compared to the recursive method. Ultimately, the recursive DFS method is preferred for this problem due to its natural alignment with the hierarchical structure of an N-ary tree. The recursion mirrors the way the tree is structured, making the implementation concise and easy to follow. With a time complexity of O(n) and space complexity of O(h), it is efficient for most use cases, as the space required is proportional to the height of the tree. While there is a risk of stack overflow for very deep trees, this is rarely a concern under typical problem constraints, especially for balanced trees. In contrast, both iterative DFS and BFS require additional data structures, such as a stack or queue and a map, which increase memory usage and add complexity to the implementation. The key observation here is that recursive DFS not only simplifies the code but also effectively preserves the tree structure without introducing unnecessary overhead. For these reasons, recursive DFS is the chosen strategy, as it strikes the best balance between simplicity, efficiency, and clarity for cloning an N-ary tree. To solve the problem of cloning an N-ary tree, we need to create an identical copy of a given tree, maintaining its structure, values, and connections. An N-ary tree is a tree where each node can have up to n children, and each node is defined by a value and a list of child nodes. We'll approach this problem using a recursive depth-first search, or DFS, which allows us to traverse the tree node by node while creating a copy of each one. First, we handle the base case. If the input node is null, meaning the tree is empty, we simply return null. Next, for each node, we create a new node with the same value as the original. Once the root copy is created, we move on to recursively copying all the children of the current node. The result will be a new tree with the same structure, starting from the cloned root node. After creating a copy of the current root node, we handle its children. For each child in the original node's children list, we recursively call the clone function. This ensures that each subtree is independently cloned, preserving the hierarchy of the original tree. The return clones of these child nodes are then added to the children list of the new node we're building. Once all the children of the current node are processed, we return the new node. To initiate the cloning process, we call this function with the root node of the original tree. This approach works seamlessly because an N-ary tree is inherently recursive in structure, with each node and its children forming smaller subtrees. By processing each node and its children recursively, we can maintain the integrity of the tree's layout. This method also handles edge cases like empty trees, single-node trees, or trees with varying numbers of children per node, ensuring that the algorithm is robust. The input to our algorithm is an N-ary tree, which consists of nodes that have a value and a list of children. The output is a new tree that is a deep copy of the original. Interestingly, we don't need additional data structures for this approach, as the recursion stack itself handles the traversal and keeps track of the nodes being processed. Now, let's analyze the complexity of our algorithm. The time complexity is O(n), where n is the total number of nodes in the tree. Each node is visited exactly once, and its children are processed in constant time per child. The space complexity is O(h), where h is the height of the tree. This accounts for the maximum depth of the recursion stack during the traversal. With this efficient design, we ensure that the algorithm scales well for a variety of tree sizes. The Python implementation of the cloning algorithm begins by defining a simple node class with a value and a list of children. In the clone_tree function, we first check if the input root is null. If it is, we return null. Otherwise, we create a new node with the same value as the root. Next, we iterate through the children of the original node, recursively calling the function on each child. The clone child nodes are added to the children list of the new node. Finally, we return the newly created root node, completing the cloning process. Let's examine a concrete example to see how this works. Given an input tree with the root node 1, which has 3 children, nodes 3, 2, and 4, and node 3 having a single child, node 5, we start by cloning the root node. We then process its children, cloning nodes 3, 2, and 4, and recursively cloning node 5 as the child of node 3. These clone nodes are attached to the new root, reconstructing the tree structure. The output of the algorithm is a clone tree that is identical to the input tree. For our example, the clone tree has the same structure. The root node with value 1 has 3 children, nodes 3, 2, and 4, and node 3 has its child node 5. Every value, connection, and hierarchy in the tree is preserved, ensuring that the clone is a true deep copy of the original. This demonstrates the effectiveness of the recursive DFS approach in handling the cloning of complex N-ary tree structures. By focusing on each node and its children in isolation, the algorithm ensures accuracy and consistency throughout the entire tree cloning process. This solution implements a recursive depth-first search (DFS) approach to clone an N-ary tree. The goal is to create a new tree that is identical to the given one with the same structure and values. Explanation of the code. 1. Node class definition. The node class represents a node of the N-ary tree. Each node has a val attribute for its value and a children list attribute that contains its child nodes. If no children are provided, the children list defaults to an empty list. 2. Solution class and clone tree method. The solution class contains the clone tree method, which performs the cloning operation. 3. Base case. The first step in the clone tree method checks if the input root is none. If the tree is empty, the function returns none immediately. This handles the edge case where the input tree has no nodes. For node creation, if the root is not none, a new node is created using the node constructor, initializing it with the same value as the current root node. At this point, the new underscore node has no children. 5. Recursive cloning of children. The method iterates over each child in the children list of the current root node. For each child, it recursively calls cloneTree, cloning the subtree rooted at that child. The cloned child is then appended to the children list of the newly created node, new underscore node. This ensures that the entire subtree structure is replicated. 6. Return the clone tree. Once all children of the root have been cloned and added to the new underscore node, the method returns the new underscore node, which represents the root of the clone tree. ### complexity analysis. Time complexity. The function visits each node exactly once, and for each node, it processes all its children. This results in a time complexity of O(n), where n is the total number of nodes in the tree. Space complexity. The space complexity is O(h), where h is the height of the tree. This is due to the recursive call stack. This implementation is concise, handles edge cases like an empty tree, and ensures that all nodes and their connections are cloned correctly. Here, we start by defining the structure of an N-ary tree node. Each node has a value, represented by the val field, and a list of child nodes stored in the children field. The class provides three constructors: a default constructor initializing the node with a value of 0 and an empty list of children, another constructor that allows setting just the value while still initializing the children as an empty list, and a third constructor to initialize both the value and the children list directly. Below this, we define the solution class, which contains the method cloneTree. This method takes the root of an N-ary tree as input and returns a deep copy of the tree. The first check we perform is to see if the root is null, which would mean the tree is empty. In that case, we simply return null since there's nothing to clone. If the root is not null, we proceed to create a new node with the same value as the root using the constructor of the node class. This ensures that the new node starts with the same value but has an empty list of children. To complete the cloning process, we loop through each child node of the original root. For every child, we recursively call the cloneTree method to create a deep copy of that child. The resulting cloned child is then added to the children list of the new node. This recursive process ensures that the entire tree is cloned, including all descendants of the root. Finally, once all children have been cloned and attached, we return the new node, which represents the root of the fully cloned tree. Let's start with example 1, where we're given a simple tree with one root and two children. The root node is labeled 1, and its children are nodes 2 and 3. First, we make the initial call with the root node, represented as node 1, node 2, node 3. We check if the root is none, but since it isn't, we proceed to create a new node with the same value as the root. This gives us new underscore node equals node 1. Next, we move on to clone the children of this root node. The first recursive call is made for the child node labeled 2. In this recursive call, the current node is node 2. Again, we check if the root is none, which it isn't, so we create a new node, new underscore node equals node 2. Since this node has no children, we return the newly created node 2 to the previous level. Now, we proceed with the recursive call for the next child, node 3. Here, the current node is node 3. Just like before, we check if the root is none, which it isn't, and then create a new node, new underscore node equals node 3. Node 3 also has no children, so we return node 3 back to the previous level. At this point, we've finished cloning both children of the root node 1. We add these cloned children, node 2, node 3, to node 1, and return the fully cloned tree, which looks identical to the input tree, with the structure, root 1 and children 2 and 3. Now let's look at example 2, where the tree has nested children. The root node is again 1, with children 2, 3. However, node 3 has its own child, node 4. We begin with the initial call for the root node, represented as node 1, node 2, node 3, node 4. Checking whether the root is none, we find that it isn't, so we create a new node, new underscore node equals node 1. Then, we move on to clone the children of the root node, starting with a recursive call for child node 2. In this recursive call, the current node is node 2. Since it isn't none, we create a new node, new underscore node equals node 2. Node 2 has no children, so we return the newly created node 2 to the previous level. Next, we proceed with the recursive call for child node 3, which is represented as node 3, node 4. As usual, we check if the node is none, and it isn't. We create a new node, new_node equals node 3. Because node 3 has a child, we now make another recursive call for its child, node 4. At this point, the current node is node 4. Again, this node is not none, so we create a new node, new_node equals node 4. Since node 4 has no children, we return node 4 back to the previous level. Then, we add this clone child, node 4, to the clone node 3. After adding the clone child to node 3, we return the completed node 3 back up the recursion stack. Now we're back at the root node 1. At this point, we've finished cloning all its children, which are node 2, node 3. We add these clone children to node 1 and return the fully cloned tree. The final structure of the clone tree matches the input tree, with root 1, children 2 and 3, and node 3 having its own child, node 4. Lastly, let's briefly consider how the function handles an empty tree. In example 3, the input tree is none, meaning there is no tree to clone. On the initial call, the root node is none. The function immediately checks whether the root is none, and since this condition is true, it simply returns none. The final clone tree is also none, as there was no input tree to begin with. The time complexity of the solution is O(n), where n represents the total number of nodes in the N-ary tree. This is because each node is visited exactly once during the traversal. To break it down further, for each node in the original tree, we create a corresponding new node, and this operation takes constant time, or O(1), per node. Additionally, the recursive function makes a call for each child of a node. If a node has k children, the time taken will be proportional to the sum of the time spent processing each child. Since this structure forms a tree traversal, the result is that we visit each node exactly once, processing its value in children. This cumulative process confirms that the overall time complexity for cloning the tree is O(n). The space complexity of the solution is O(n), where n is the total number of nodes in the tree. Let's understand why. First, the recursion depth depends on the height of the tree. In the worst-case scenario, such as a completely skewed tree, the height could be O(n), meaning the call stack would require O(n) space. In the best case, for a perfectly balanced tree, the height is O log n, so the call stack would use O log n space. Additionally, we allocate memory for the clone nodes themselves. Since each node in the original tree has a corresponding new node, this also requires O(n) space. When we combine these factors, the overall space complexity is dominated by the recreated nodes, leading to a total of O(n). Analyzing the best, average, and worst-case scenarios, we observe consistent O(n) time and space complexities. In the best case, if the tree is balanced, the recursion depth is O log n, but since there are still n nodes to process, the time complexity is O(n), and the space complexity remains O(n), dominated by the clone nodes. In the worst case, such as a skewed tree resembling a linked list, the recursion depth becomes O(n), and the total nodes are still O(n), resulting in O(n) time and space complexities. The average case for a general tree also follows the same O(n) complexity for both time and space. Comparing to a naive approach, which could involve manually traversing and reconstructing the tree without recursion, the optimized recursive approach is not only simpler but also optimal in terms of time and space. While an iterative approach using a stack or queue could achieve the same O(n) complexities, the constant factors might differ. Ultimately, the justification for both time and space complexities comes down to the fact that each node in the tree is visited exactly once, and the memory usage is predominantly determined by the number of nodes, which leads us to O(n) for both metrics. When working on cloning an N-ary tree, there are a few common mistakes to watch out for. First, not handling edge cases like an empty tree can lead to issues such as null pointer exceptions or runtime errors, especially in recursive solutions. To prevent this, always include a base case to handle null or empty input explicitly. Another mistake is improper node mapping during cloning, where the same node reference is used for both the original and clone trees. This can cause unintended modifications to the original tree when the clone is updated. The solution here is to always create a new node for the clone and avoid reusing references. Lastly, inefficient traversal, such as recomputing the same subtree multiple times, can drastically increase time complexity. To address this, use memoization or a hash map to store already visited nodes, which ensures that redundant work is avoided. Additionally, a frequent oversight is skipping children while cloning an N-ary tree. Forgetting to loop through all the children of a node leads to incomplete cloning, or entire subtrees might be missed. To fix this, ensure that the children list of each node is fully iterated. Another common issue is incorrect base cases in a depth-first search. Many assume the base case applies only to leaf nodes, but this can cause the recursion to terminate prematurely for nodes without children. To resolve this, make sure the base case accounts for null nodes while also ensuring proper traversal of all child nodes. These adjustments help produce accurate and complete tree clones. Now, let's consider some interview strategies and insights. First, it's crucial to understand the problem scope. Determine whether the tree is binary or N-ary, as this affects how you handle child traversal. Testing thoroughly is another key point. Be prepared for edge cases like null trees, single-node trees, or trees with deep hierarchies. It's also important to think about recursion versus iteration. Recursive depth-first search is often intuitive, but for wide trees, iterative breadth-first search with a queue can be more memory efficient. Finally, optimizing with hash maps is essential when the tree involves cross-references or potential cycles. This prevents infinite loops by tracking visited nodes, making your solution robust. To deepen your understanding, it's helpful to explore related problems. For example, LeetCode 133, Clone Graph, applies a similar concept to graphs and introduces the challenge of handling cycles. Another relevant problem is LeetCode 138, Copylist with Random Pointer, which also emphasizes mapping old nodes to new ones. For practice with recursive traversal, LeetCode 559, Maximum Depth of N-ary Tree, is a great exercise. Additionally, LeetCode 105, Construct Binary Tree from Pre-order and Innerorder Traversal, reinforces tree construction and traversal logic, which can complement your understanding of cloning tree structures. Finally, let's look at some alternative approaches to cloning an N-ary tree. Recursive depth-first search is a straightforward method that's easy to implement, but it comes with the trade-off of potential stack overflow for very deep trees. Its time complexity is O(n), where n is the number of nodes. Another option is iterative breadth-first search using a queue. This approach avoids recursion depth issues and is more memory efficient for wide trees, though it also has a time complexity of O(n), and requires additional space for the queue. For problems involving cycles or cross-references, using a hash map to map original nodes to their clones is essential. While it adds O(n) space overhead, it's a crucial tool for handling more complex tree or graph structures, such as those found in the clone graph problem. Great job working through this problem. To summarize, we used a recursive DFS approach to clone an N-ary tree efficiently. This problem reinforces key concepts in tree traversal and manipulation. Remember to practice regularly to build confidence. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!